Alrighty here, so let's look at page 264, example 1, and it has something a little more interesting. Let's write it how they have it written there. So v of t, the velocity function, is t squared. Okay, the velocity function is t squared, and this is our regular old parabola, and we're going from t equals 0 to 3. So we're getting a little more abstract here, right? I'm not using any units here, and the problem in the book just says that you have some particle traveling along the x-axis, which they never do. They never behave that well. So this is a little more abstract, but it's the exact same idea. I'm going to take this velocity function, and I'm going to find the area underneath it between, t equals 0 and 3. So let's consider this parabola between 0 and 3. So from 0 to 3. So at 0, 0 squared is 0. At 1, 1 squared is 1. I'm going to kind of compress my y-axis a little bit because these numbers are going to get bigger faster, obviously. At 2, we're all the way up to 4. Okay, and at 3, we're all the way up to 9. So 4, 5, 6, 7, 8, 9. At 3, we're all the way up to 9. And here is my parabola. Okay? And if I want to find how far this particle traveled on these abstract units or whatever, I need to find the area underneath this curve. Well, those last two shapes I know. I knew the area of a rectangle is length times width. I know the area of a triangle is 1/2 base times height. We made it with the trapezoid. We have formulas for all those. We don't have a formula for this. We don't have a formula of a kind of a triangle with a parabola side to it. So what we're going to do here is guess. Kind of. We're going to approximate this by saying, well, these are not rectangles. But what we're going to do is we're going to throw some rectangles in there and see what happens. And what I'm going to do, and hopefully you'll just go with me for a minute here, I'm going to look right in the middle of each of these. I'm going to look right in the middle, here, here, and here. And what I'm going to do is I'm going to draw some rectangles at that middle point. So at this middle point, it'll be right there. At this middle point, that will be right there. And at this middle point, that will be right there. And just hang out with me for a minute. I'm going to draw some rectangles at that middle point. And why rectangles? Well, rectangles are easy. Okay, and this is really just going to be an approximation, but it should be pretty close. Okay, so you can see I drew 3 rectangles here, with the middle of the rectangle coming up and hitting the line. Okay, this is, well, MRAM. Okay, midpoint, rectangle, approximation, method. And I got bored of making my words come down, so I made that one off to the side. So the midpoint rectangular approximation method, or we'll just abbreviate it, MRAM, means go up until the middle of the rectangle hits the line. And I use rectangles because rectangles are easy to work with, okay? So let's see. Ooh, little ant there. Got him. Good. Whoops. Oh, no. Sorry, ant. Anywho. So let's find the area of these 3 rectangles. And I think midpoint is a pretty good approximation here because you see I missed this part of the curve, but kind of adds in this little extra bit right here. So it's like those parts would kind of cancel out. It wouldn't be exact, but I think we're going to get pretty close. Those parts right there and those parts right there. So let's go ahead and try to find the area of these 3 rectangles. Well, let's call these rectangles 1. Okay, that's rectangle 2, and that's rectangle 3. Okay, so for rectangles 1, 2, and 3, well, the area of the rectangle is length times width. Okay, well, let's call this the width right here. The width of each of these rectangles is 1. So 1, 1, 1, and I made it 1 on purpose, so that would be easy later on because I knew I was going to do this. The length, or I guess the height of the triangle, well, this is at 0.5, this is 1.5, and this is 2.5. So I need to square each of those to see where they would hit the line. So 0.5 squared. At 2, that would be 1.5 squared. At 3, the third rectangle here, well, that's 2.5 squared. Okay, so length times width. So the area of each of these rectangles, well, 0.5 squared, that's 0.25 times 1 is 0.25. 1.5 squared, that would be 2.25. I know 15 squared is 225. So 2.25. Okay, and this last rectangle here, 2.5 squared, that's 6.25 times 1 is 6.25. I know that 25 squared is 625 as well. So let's add these up, right? I found the area. The area of this first rectangle here is 0.25. The area of this rectangle is 2.25, and the area of this rectangle is 6.25. So let's add up these three areas, and that will give me an approximation of how far this particle traveled. Okay, so let's add these up. Let me see. 15, 1, 2, 3, 4, 5, 6, 7, and 6, 7, 8. So 8.75. So over this time, if this particle is traveling at the velocity t squared, and this is my rate, and this is time. Okay, well, the area under this curve is going to be pretty close to 8.75. Okay, in your homework assignment, go ahead and try problems 1 through 8. There is a problem there that will tell you to get a calculator to do some calculations for you. We'll go over that together. So go ahead and do what you can of problems 1 through 8. I haven't found a TI-83 program, but we'll do it. We'll do it using some internet. And if you can find something on the internet to do that, more power to you.